Hello everyone, welcome to Math Fables, and in today's video of functions what we will do is learn about inverse functions. So let's get started. So what is an inverse function? The inverse of a function is the function that undoes what fx has done. We write the inverse of the function fx as f to the power minus 1x. So as you can clearly see from here, as you can clearly see from this diagram over here, the domain of fx is actually the range of f inverse x, and the range of fx is actually the domain of f inverse x. So what does that mean? So let's say we have x is equals to 2, and if we apply fx, the function fx, then this gets resulted into, let's say, 5. Now let's say we have y is equals to 5, and if we apply f inverse x, it gets converted to back x equals to 2 again. So what we really see over here is a cycle where f is converting one form to another form, and f inverse is converting that form back to its original form. So that is why the ultimate or net effect of f inverse x is actually 0. The net effect is 0, which means that x remains as it is. It has no change. Again, similarly, instead of starting the cycle at f, we could also start the cycle at f inverse, right? So f inverse fx, and we would get the same result, which you can see is being given here. So as we can see from the diagram, the domain of f inverse x is the range of fx, and the range of f inverse x is the domain of fx. However, it is important to note that not every function has an inverse. So what do we mean by that? So in our last video, what we had learned is that there are two types of functions, right? We have one-to-one function and many-to-one function. So what we really need to note, and that is very important, is that only one-to-one functions have a inverse function. If it is a many-to-one function, it will not have an inverse function, and we can clearly see why. Here I'll show you why. So let's say we had two variables x, right? We had two variables x2 and 7, and both through the function fx gave us the variable y is equals to 5. Now 2 is being mapped onto 5, and 7 is also being mapped onto 5 by fx. Now if we apply f inverse x, so let's use a different color for f inverse x. Now from 5, where do we go? We know that if we have a value like this, if we have a function like this, it can only give us one value, right? So from 5, do we go to 2 or do we go to 7? How do we know this? We cannot know, and that is exactly why if it is a many-to-one function, we do not have a f inverse. So what do we have instead? Instead, what we could have done over here is that if we said that if we had restricted the domain of fx, if we had restricted the domain of fx and said that x can only be from 3 to 100, what does that mean? It means the variable 2, which was previously in the domain, does not exist anymore. We only have the variable 5. And since we only have the variable 5 which is being sorry, I think the variable was 7, right? So now if we only have the variable 7 which is being mapped onto 5, we can simply then use the function f inverse x to reconvert it back to f 7, right? So in that is what we can do. So one-to-one function has an inverse, many-to-one function does not have an inverse. However, how can we ensure that many-to-one function has an inverse? If we restrict the domain, that is, if we convert it into a one-to-one function by limiting the domain. So let's see a graphical representation of this. For that, let us move to the, okay, let's do it over here. So let's say we have a many-to-one function like this. Oh, this is still a one-to-one function. Yes, let's say we have a many-to-one function like this. So over here, as you can see, let's say this is our turning point on the y-axis. So let's say it is cutting the y-axis at -1. This is 2. This is -2. So as you can see over here, from 0 to 2, this part over here, that is a one-to-one function, right? Because over here for each value of y, there is only one value of x. However, the moment you go a little to the left, the moment you, let's say, consider the values of x till this point, then for this value of y over here, you have two values of x. So it becomes a many-to-one function. So how can we make it a one-to-one function? We can do it in two ways. We can split the graph into two parts. We can split the graph into two parts, and either we can take only this part or we can take only this part. And each of these separate parts is a one-to-one function that will have an inverse, but this entire expression does not have an inverse. So the domains that will have an inverse is x is greater than or equals to 0, or x is less than or equals to 0. So this part has an inverse, this part has an inverse, but the entire thing does not have an inverse. We could have used other expressions too. It could have been anything like x is greater than 2. It will still have an it will still have a inverse. It could have been anything from 5x to, it could have been 709 x 0. It could have been anything like that. Anything that falls within this domain, okay? As long as it does not cross over from this side and this side, by which I mean that it is solely contained within one side of the region, it will have an inverse. Now let's look at a more complicated diagram. So for that diagram, our turning point for the previous diagram was 0, comma, -1. So we could have easily identified it, right? Instead, let's say we have an equation like this. What do we do now? We have an equation like this, and let's say over here our expression is fx is equals to x square minus 4x plus 8. So what do you do in this case? How do you split the graph into two regions that will be one-to-one functions? So what you do over here is basically we do completing the square, because we need to find the turning point. So if we do completing the square, we can see that x square minus 2 into x into 2 plus 2 square minus 2 square plus 8. So we will be left with x minus 2 whole square minus 4 plus 8. So that is plus 4. So from here we know that the coordinates of the turning point is 2, 4. So this diagram was slightly wrong. So I will make you a better diagram. So in this case, our diagram is something like this, where these are our turning points, right? So once you have found out the coordinates of the turning point, now it is pretty easy. You can see it from here how to split it, right? So one region will be x is less than 2, less than or equal to 2, and another region will be x is greater than or equals to 2. And any domain values that solely contain one side, either this side or that side, either this side or that side will have a inverse function. However, the moment a function is covering, let's say, the entire of this side and even a little portion from this side, which is it spilling over to the other side, it will not have an inverse anymore. So I hope that part is clear. Similarly, if instead of a quadratic equation, if it was a polynomial, right? If it was a polynomial with, let's say, something like this. So how could you split it? So you might be given this in a graph, and from the graph, you know the coordinates of this point, you know the coordinates of this point, you know the coordinates of this point, and you know the coordinates of this point. Then easily you can split it. So one region will be, so how do you identify the region? You basically take the turning points and then you draw a line parallel to the y-axis through the turning points. So over here we have 1, 2, 3, 4 turning points, and we drew lines parallel to those turning points. And the region between any two turning point is a one-to-one function. So any domain that is contained within any of these one values is a one-to-one function, and it will have a inverse, right? So as you can see over here, the region between two turning points, I'm marking it. These are the points which will give a one-to-one function. However, the moment the domain crosses from this side to even a little bit from this side, it is no longer a one-to-one function. It becomes a many-to-one function, and then it will no longer have an inverse. So you see the graphs, you identify the turning points, and then you split the region, and you will understand whether if the turning points are contained within the domain, it will not have an inverse. If the turning points are not contained within the domain, it will have an inverse. Now, moving on to the next part. How do we find an inverse function? So since we have already known that there is an inverse function, we also need to know how to find that inverse function. So there are three basic steps. First, we will rewrite fx as y. Step 2, we will make x the subject and express it in terms of y. And step 3, we will replace x with f inverse x and y with x. So what do we mean by that? Let's say we have function fx is equals to 3x plus 5, right? So over here, we go to step 1. What does step 1 say? We write fx as y. So before we can write fx as y, we need to write one statement. This is usually a marking point, so make sure you write this statement. What do we write? We write let fx be y. Instead of y, you could have used any other variable. That is not an issue. So then we have y is equals to 3x plus 5. So now we go back to step 2. What does step 2 say? We make x the subject and express it in terms of y. So right now y is the subject. So how can we make x the subject? We do some simple algebraic manipulation. So one second. Okay. So how do we make x the subject? So we do some algebraic manipulation. So 3x becomes y minus 5, and therefore x is y minus 5 divided by 3. So now we have expressed x in terms of y. So our step 2 is done. We move on to step 3, which is replace x with f inverse x and y with x. So f inverse x becomes x and y becomes x. So that becomes x minus 5 by 3. And now you have an expression for f inverse x. Now if you want to check whether it is actually what happens, let's see it. So let's say we take x is equals to 1, right? X is equals to 1. So f1 gives us 8. Now let's say we take f inverse of 8. And what do we end up with? 8 minus 5 divided by 3. That is 3 divided by 3. And then we end up with 1. We are back at square 1. And that just shows that our calculation has been correct. So you can do these little tricks and tricks here and there to check your works along the way. Now, moving at a little bit more complex example, let's say it was a many to one function, right? Let us take the equation that we had given earlier, which was x square plus 4x plus 8, and we now have to find the inverse of fx. So now we cannot find an inverse of fx, but they have told us that x is less than or equals to 0. So since they have told us x is less than or equals to 0, now we know that it is a one-to-one function and it does have an inverse. So how do we find that inverse? So before we find that inverse, what we do is, again, we do this completing the square, and from the completing the square of last time we had gotten, it is x square x plus 2 whole square plus 4. Now we will replace fx with y. So we will write let y is equals to fx, and then y is equals to x plus 2 whole square plus 4. Now we need to express x plus 2 whole x in terms of y, right? Which is our second step. So x plus 2 whole square is equals to y minus 4. X plus 2 is equals to plus minus. Do not forget the plus minus at this stage. You need to include both of this. It is a very common mistake of many students. Make sure you include both the plus minus, and then x is equals to minus 2 plus minus root over y minus 4. Now you have been given that x is less than or equals to 0, right? Since x is less than or equals to 0, we only take the negative value for the expression of f inverse x. So while you're converting to f inverse x, that is when you do not keep the plus minus anymore. So over here, we only take the negative value because we have been given that x is less than or equals to 0. So now we only take the negative value and we write it minus 2 minus x minus 4, and that is our inverse function. However, let's say this was not the condition. What if the condition was x is greater than or equals to 3. If the condition was x is greater than or equals to 3, then this would be wrong. In that case, f inverse x would be minus 2 plus root over x minus 4. So that is something you need to be very careful with. Now let us look at a very special scenario. What if we found out the inverse of fx and we resulted in an expression that is exactly identical to the expression we started with? That is, what if f inverse x is equals to fx? What then? That is a scenario where we call that it is a self-inverse function. So how does a self-inverse function look like? A self-inverse function is basically a function which is symmetrical about the line y is equals to x, right? And the graphical implications of it we will get to know right now. So nothing to worry about. So here we have the graphical representation of inverse functions. The graphs of f and f inverse are reflections of each other on the line y is equals to 0. Something really important. So why is it? Because this is because f inverse x is equals to x is equals to f inverse of fx, right? We have already talked about this over here. Now if you see in the y-axis, what do we input? In the y-axis we input, while we're drawing a graph of fx, we input fx over here and we input x over here. If we are drawing a graph of fgx, we input fgx over here. We put fgx over here and we put x over here. Similarly, if we are drawing a graph of f inverse x, we put f inverse x in the y-axis and we put x in the x-axis. So, when we are graphing, we can say that f inverse x is equals to y, f inverse fx is also equal to y. So, the line of symmetry is y equals to x. I hope that is clear. So here we have an example that has also been taken from the course book. So over here we can see that at the beginning we were given a graph this and we were asked to find the inverse of that graph. So how do we find the inverse of that graph, right? What we do is simply we will draw the y equals to x line first. That is our very first thing to do. So let's draw a line through y is equals to x. It will be somewhat like this. And now we simply use these coordinates. As we know that an inverse function reverses the x and y coordinates, which is it inverses the domain with the range, as we have already seen. Over here the coordinate is 1 comma minus 2, right? So if we do the inverse function of this, if we do the inverse function of this, what will we be left with? After the inverse function has been given, the coordinates will be turned into minus 2 comma 1. So now this will be our next plot. So that is minus 2 comma 1. Again, over here you see this point is basically 3 comma 7. So we have 3 comma 7, and if we have to apply the inverse, it will be transformed to 7 comma 3. So then you plot the point 7 comma 3. So we can see that it is this point. And again, since y equals to x is the line of symmetry, it will always pass through the point where the fx graph is intersecting the y is equals to x point. So now all you need to do is you have to join these 2 points, make it look as similar to the previous one. The more I just considered 3 points over here, the more points you will consider, the more accurate it will be. And as you can see, if we plot the f inverse x, it is exactly the same and you get the full marks. So now I have taken a small exercise from the course book for us to do together. So I will be scrolling down. I hope every one of you will pause the video for a while and try to attempt it on your own, and then you can resume it back again and we can do it together. So let's get started. The very first thing that we do always when we're plotting the inverse is we will draw the graph, we will draw the f equals to x line. So here we have a f equals to x line. Here we have another f equals to x line, as you can see. So we will repeat this for every one of the graphs that we have to draw. It was a little off, so I'm trying to fix it. Okay, it's not very perfect, so I'm going to just delete it altogether. So guys, pause the videos and I'll be back. So I hope you guys have copied the diagrams in your copies and now you have been able to finish all of that, and so we will check now. Right. So for the first diagram, again, what we do when we are drawing the inverse, when you have a question like that, how will we proceed? So at the very beginning, we first determine whether it is a one-to-one function or if it is a many-to-one function. So over here, as you can see that it is very clearly a one-to-one function. This is also, part B is also a one-to-one function. Is part C a one-to-one function? Yes, it is, because as you can see, for each value of y, there is only one corresponding value of x. So yes, it is also a one-to-one function. However, here for every value of y, there is only one value of x. So it is a one-to-one function. However, as you can see, for part D, for each value of y, there are two values of x. Even here there are two values of x. Even if in any one point for a value of y there is two value of x, this is no longer a one-to-one function, this is a many-to-one function, and so it will not have an inverse. So the rest of the ones have an inverse. So how do we draw the inverse functions? We first draw the line y is equals to x. We first draw the line y is equals to x, and then we find out the coordinates of this coordinate, right? So it is 5 comma 2, so this coordinate will become 2 comma 5, so this will be converted to over here. So that is our point. Then over here we have the point minus 5 comma minus 3, so this will be converted to minus 3 comma minus 5. So we have minus 3 comma minus 5, so that is our point. And then we just need to sort of join the points, which is obviously not being okay over here. Hence I have the drawing right below for you guys to check, but you all understood the procedure, right? So now I can show you the diagrams for you to check. So here is our very first diagram. As you can see, we drew the line y is equals to x, and then we just found out the inverse. Now Moving on to the second one, which is part B. So for part B, again, you can see we drew the line y is equals to x, and then we simply inverted the coordinates and joined the points. And lastly, we have our last diagram of today, which is part C, and again we drew the line y is equals to x and simply we inverted the coordinates. We need to make sure here are some things, as you can see, you need to make sure while you're drawing it. I will bring it up little further up. Okay. So as you can see over here, the point where the graphs cross intersect at the line y is equals to x, this is same for all three graphs. You need to make sure for this you will have marks. The x intercepts and the y intercepts, you need to be careful with how they're changing. And then if you look at a property of this graph, how can you see that y is equals to x is actually the line of symmetry, except the fact that obviously this point is being converted over here and you can see there is a symmetry from the line y equals to x. There is another way you can figure it out, that is if you connect this point to the point that it was inverted against. So this was the point from the original graph and this is the point from the inverse graph. You see that if you join a line perpendicular to it, this line will always be if you join a line connecting these 2 points, this line will always be perpendicular to the line y is equals to x. Or in other words, any line that connects a point from fx to the corresponding point of f inverse x, that line has the following equation: y is equals to minus x. Right? Y is equals to minus x plus c, because it is being translated at different points. It can be here, 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 but the general equation is y is equals to minus x plus c. However, this is not a knowledge that you will be tested upon or you need to know. This is just some additional information to clear your concepts. And with that, we close our chapter on inverse functions. In the next video, we will be looking into the graphical representations of the different functions and what games and play on it we can do. So I hope you're excited for it. Goodbye for today.